All right, this is not on yet. There we go. All right. So, do you guys enjoy the career fair? Those of you who went? Good. I know there was, excuse me, a few people that reached out to say, forgot about the quiz or something like that. I tried to be clear in class and with the email that it was going to be open Thursday and Friday for you if you were going to the career fair. But if you did it, if you followed along and you just didn't submit the quiz, or whatever, you can email me, and I will this time give just a bit of credit for that. See that you're participating and aiming to learn. That's what I'm caring about with the participation activities, and I'll be posting more like that. Given that my sort of default, what I had some material set up for was that Kahoot thing, and now they're just gonna charge me money to actually do it for 50 students. I'm abandoning that and going to just go only to these Moodle type quizzes. So that'll be the type of thing. I'll cover something in class. We'll talk about it. Maybe start solving a problem, or maybe I'll give you a reading assignment, and it'll complement the topic, but not in a way that I want to test you on that with the exams, but something that is kind of a little supplemental. So that's the type of thing that I'll be doing for you. Okay, so we left off last time talking about this problem, and I gave that to you as an assignment. And I posted these notes, so you had this as kind of a starting place. This is basically a flocculation, and I had you solve it. I changed the numbers a little bit to say 0.015 millimeter particles. And I basically asked you to find the diameter of the final particles if these particular ones were put in a flocculation chamber as described. Okay, so we'll walk through the main pieces of this, and then I'll kind of put the last pieces together with you and show the calculations I have in Excel to get the answers and show you the final answers for the problem. After that, we'll get into a little bit of granular filtration, which will be the next topic after the coming exam. So we have an exam in 1 week. Thursday will be a review session. I'll go over the homework solutions for the homeworks you've done so far, and any questions you have then. So that's kind of the plan right now. All right, so we'll come to this problem. We said that really we've got all these equations that we covered for flocculation, the mixing intensity, this K that we need some rate constant to describe how often the particles will stick together. And to solve that, we need that mixing intensity, and we need some flock volume, which is a portion of the water that's occupied by the actual particles. So with all of that, we can find this rate constant. And once we have that rate constant, then we can put it into a mass balance like we've been learning about. So with a mass balance on reducing the number of particles means they're sticking together, means we have fewer larger particles. So that's the whole point, and that's kind of what I wrote up here is the G, the K, the omega. We drew our mass balance. We noticed that we have some total flow. Half of it's going through one chamber, half the next. Those are identical, so we can just kind of narrow our focus into one, and if we find out what's happening to one, we know what's happening to the particles in either of them. And so we'll know something about the nature of the particles leaving both chambers in that sense. Okay, so then we go to set up a mass balance. We assume it's operated enough time, it's reached equilibrium, so it's at a steady state. So we can then solve our steady state mass balance on just one of these CSDRs, such that the Q going in times the number or concentration of particles going in, that's our input rate, minus the Qn leaving is our output rate. And then we have a reaction term for the particles sticking together. That's this minus VKN. So that's kind of the mass balance setup, and then we want to solve it. A lot of times we solve for N over N naught. In this particular case, it makes a little more intuitive sense to solve for n naught over n, because that's how many of the initial ones are in each of the final particles. That gives us a way to relate the size in a very straightforward manner. Okay, so then we can do that, simplify our solution, and we really get this solution right here where n naught over n is just 1 plus theta k. So then we need our theta. We can solve for the theta is v over q. We are given the volume and the flow rate. The volume was, I think it was 3.5 cubed. And the flow rate was half of the total, which the total was 3, so that would be 1.5 mgd, which we would have to convert to meters and maybe seconds. Okay, so that would give us, though, a theta. Once we were to solve for that, we also have to solve for the k. Putting all that together, we should be able to solve for the n naught over n. From there, we make a comparison between the volumes. Okay, what's the volume of the initial particle? We can calculate that based on the volume of a sphere. And then we assume that they join together and make a new spherical particle out of this aggregate, just becomes a new sphere, but conserving the same amount of volume. And then we can calculate the volume of that new sphere. And that's the way we can get at the diameters, because the volume of a sphere depends on the diameter. So that's the full circle of the problem. Several things we needed to solve for along the way: this mixing intensity, the omega, the k, the n naught over n, and the diameter of the aggregate. Okay, so I'm going to skip forward a little bit. I've got another blank slide for this where we can work that out. We also talked about the sequential reactors, comparing that to side-by-side reactors. Talked a little bit about that problem. I'll make a comment on that in a minute. But this is just another portion for our slide there. Okay, and I need to bring up my calculations too. Okay. All right. All right. So you should see kind of what I have here. Make it a little bigger. You see I had Q, and I solved for that Q, halved it first, and then converted it to cubic meters per second, given the conversion factor we were given. I just wrote up our value for our dynamic viscosity that was given. Our power, we needed to convert from kilowatts into watts, so that would be 2,500 watts. The volume of the basin, that's just the 3.5 cubed, is 42.875 cubic meters. And we were given an initial number concentration of particles as, I think, 100,000 particles per milliliter, 10 to the 5th. Now, we actually have to convert that per milliliter into per cubic meter in order to get our units the same across different pieces. So when we initially said n naught was 10,000 or 100,000, we actually have to convert that to 1 times 10 to the 11th particles per cubic meter. Then we can relate the meters across in order to solve our omega properly. Okay, so the last thing I'll say is we had our diameter of the particle. That was 0.015 millimeters. That becomes 1.5 times 10 to the minus 5th meters. So I've got that there. So then we go on to put these into play. And so for our G, we would say G, that's the square root of the power input divided by the dynamic viscosity divided by the volume of the basin. And putting in the 2.5 kilowatts and converting that to watts, we should get, what was it, 225, I believe, or 226 per second. Yeah, 226. Okay, so that gives us G. The next thing we need is our omega. This is the flock volume, right? So this is the volume of one particle times the volume of all the particles, or the number of particles per concentration. So this is going to be the N naught times the diameter of the particle cubed times pi over 6. So when we put that in, recognizing that we need the diameter in meters and the number concentration also in meters, that should then give us this value here, which I'm going to convert to scientific notation. So 1.77 times 10 to the minus 4. There's no units on that one because it's just a portion, right? It's like 0.00177% of solution is particles. Okay, so then that gives us the ability to solve for K. You recall that's going to be that collision efficiency. The collision efficiency was inferred to be 1 because we were told it's completely destabilized. If I can find the cursor. That tells us that this, this term is 1. If it was partially destabilized, then we would need to find some number for that, or be given a number for that. Okay, so that we've got that times 4. What is this? This is times the G. And just because I don't forget all the way, yeah, 4 omega G over pi, that's right. Okay. And given that, we can add in all of our pieces and say, when we solve for K, that K is going to be 0.05 per second, maybe 0.051. Okay, so far this is just sort of plugging things in and putting in the numbers, but with attention to converting the units properly, right? There's not actually anything too fancy about any of these pieces. So then we can also solve for theta. I mentioned that earlier. We can get the Q for one reactor. It's V over Q. And that turned out to be 652, we'll say 652.6. Okay, so now we have basically everything. We already derived earlier that the mass balance that started as a steady state Q coming in, Q going out, minus that reaction, that yields us, with some simplification, we get that's 1 plus theta K. Right, that was, if we solve for that, do the algebra, that's what we should get. And from there, now really all we have is the two numbers to plug in. So the deal with this type of problem, there's a lot of the units there to track and to handle. Then there's a matter of putting it into the mass balance and recognizing how the mass balance fits in to give us a relationship between the initial and final particles. That's what we're really looking for, is that relationship. Then we need to know how to apply that relationship. So we've got this, and in this scenario, this 1 plus theta K becomes 34.13. So there's approximately 34 of the initial particles in every one of the final ones. So we can say then that the volume of the final ones are 34 times the initial. Now we also have to account for the cubic to convert the diameter, but at least on a volume term, now we know how much is one compared to the other. So when we say the volume of an aggregate, we know that's going to be equal to 34 times the volume of the initial particle, right? Does that part make sense? Because this is the other sort of key relationship part here. Okay. So then, if we are trying to find the diameter of the particle, we can recognize that, assuming that it's a sphere, so we're just going to make the assumption that they're spheres, that's diameter cubed, pi times diameter cubed over 6. And that's not particle, excuse me, that's the aggregate. Is going to be equal to 34.1 times the diameter of the particle, which we know something about, times pi over 6. So the pi over 6, those will just cancel. And we're left with a relationship there just between the two diameters. So we can say the diameter of the aggregate should be equal to, I'm just going to take the cubed root of the diameter of the particle cubed divided by that, times the 34. All right, does that make sense? And we can solve that and get our diameter for the aggregate. Should be, we can put it into millimeters for an easy comparison, or we could leave it in meters, but here that would be 0.0487 millimeters. And if we compare that, it should definitely be larger than what we started with. What we started with was the 0.01, or excuse me, 0.015 in this. Change to that. And sure enough, it is 3 to 4 times that. So it is larger. It should definitely be less than 34 times larger because that cube factor there. So yeah, that's how we would arrive at the answer. Any questions or issues with that? Do you find it helpful to take it home and work on it at home? It's kind of like a mini homework assignment kind of a thing? Okay, good. So I'll try to set up a few more like this instead of having it just at home or just in class. That sounds like that's maybe a little quicker feedback is nice. All right. So with that, I want to talk for a moment about, well, what happens if we have it in a different scenario? So this is the typical scenario here for what would actually happen at a water treatment plant. But what if we are out, in the wilderness somewhere, we just get some muddy water and we want to just treat it. We have a few tools. We want to treat it for ourselves and then drink it. In that case, we'd probably just have a batch. So if we think about what happens in a batch system, let's imagine we just have some bucket and we can stir it for a little while and then stop stirring and let it do sedimentation. So we could think about a problem that would be, you have all the tools for here to do a batch flocculation and sedimentation, right? This is the way my brain works when I think about assigning problems, right? Or designing exams. Like, okay, you have all the tools now to do sedimentation. You have all the tools to do flocculation. You have the tools to do this in different mass balances. We covered the CSTR case. Well, how about the batch case, right? That's even simpler in some ways. So how about a system like this where we have something, I don't know, maybe 10 liters for volume. And, you know, we could make up some numbers here. We could use some of these numbers given. Let's just ignore the those pieces. And, you know, I don't know, you know, if maybe I'll walk through the steps to solve this one and not do the whole solution, but I'll sketch it up real quick as if I was creating a problem. Okay, so let's say we're gonna estimate power. We can get maybe a 2-watt motor, solar powered, you know, just something a little mechanical stir of some sort or just by hand. And let's say we decide that 10 minutes is as much as we're willing to like stir the little pot, right? I have no idea if these numbers are going to be realistic. So if you go and solve this, bear in mind that it could be a little distorted in terms of the numbers. And so that would be something I would want to check first. And let's say we have similar particles. Diameter particle would be let's say 0.02 millimeters. And what else do we need? Some number concentration of them to start with. That 10 to the 5th sounds good to me. Particles per milliliter. So we can just use the same one as last time. By the way, as an aside, I think some of you asked me this last time, that might have been the other class, but we never solved for n in the last problem. We don't really need to, typically. I guess we could, but generally we just need it as a proportion, right? So if you're finding yourself trying to solve for n in these problems, it's usually you're getting distracted, and you actually don't need that. So in this case, once we have our problem defined, and maybe there's something else we need to define, but we would think about, all right, well, how fast are these going to settle? You know, maybe that's the question is, once we do the flocculation, how long does it take before these particles settle? That could be a question that combines the flocculation with the sedimentation, right? So we would start by trying to figure out, okay, well, how big are they going to get? It's exactly the same process as last time, but now we have it in a batch system. So in a batch scenario, again, we have some K for the collisions. So we'll need to solve for the G, the omega, the K, all that, for our mass balance. And really it's the G and the omega to get the K that gets our mass balance, or that's put into our mass balance, right? You can think about it that way. And the way we'd write our mass balance in this case, since there's no inputs or outputs, in that volume we have some change in D, or in N over time, and we define that entire change just by that decay reaction between the particles. So that would be a first order decay. We've seen this before, and normally we solve it for N or solve it for N over N naught. So just as a quick reminder, the way we'd go about this, we'd simplify, get rid of the V's. We'd separate the integration parts here and say dn over n, divide both sides by n, equals negative k times dt. Then we integrate from some 0 to time t, and we integrate from some initial condition with n to some final condition, right? We want to know, we started with some amount, we're going to end with some amount, how do we compare? So the integration here, again, that's turns out to be the 1 over x dx is the natural log of x. And so we'll have natural log of n minus the natural log of n naught equals negative k times time. Here we can do some simplification. Well, first of all, the natural logs can become n over n naught. We can combine them that way. And then we could raise e to the power of both sides to get rid of the natural log, so we get n over n naught equals e to the minus kt. So here we're close, but we want to invert it. So we could invert that and say n naught over n is equal to 1 over e to the minus kt. And I think we could even take that. This should be correct, right? That should be equal to e to the kt. All right, so that gives us an equation that we can find our n naught over n. We could do the same volume comparison as last time, and we could even go all the way as far as to say, to ask ourselves, well, how long would it take for these particles to sediment, to calculate the sedimentation velocity for those compared to these new ones, right? How much change happens in 10 minutes? Is that enough? So just as a little reminder, we can calculate the sedimentation velocity, this Vs, for both, before and after that. Okay, does this make sense how you'd approach it in a batch instead of a CSTR? Kind of, this is what I was talking about early on when I'm saying these mass balances, once we handle them, we're going to see them in a lot of places, and it gives us some flexibility to do a lot of things with them. Okay, so speaking of that, I'm going to take a moment and just come back to this little problem I left you with last time. At least a couple of you went on your own time and did some solving for this particular case. And you were thinking to yourself, well, my n over n naught, or my n naught over n, wasn't really a big change here. Is that weird? Is that wrong? And this was not even a flocculation problem. This was just a generic mass balance problem. So we had some growth reaction here. All I will say is we're considering bacteria growth. And if you know anything about food safety, or if you remember back whenever you might have taken a biology class, bacteria have a doubling time that's something like, the fast ones maybe an hour, hour and a half kind of thing, right? So 90 minutes, pretty typical E. coli. So overnight or over the course of a hot sunny picnic, some bacteria growing in your food over the course of 5 or 6 hours, you can get a big problem. But let's just take a quick look at how much time we're giving these in this hypothetical here. The theta, that V over Q, turns out the volume was 8 cubic meters. So in total, in the whole system, we'll say that's 16 cubic meters. And the flow rate here was half a cubic meter per second. So even through the entire system, that's 32 seconds. So that's not very close to the doubling time, right? So if you got some answers that looked like not much happened, that makes sense, right? So I just put in some numbers here, and they're not particularly useful to actually see a big difference. But practically speaking, that actually makes a lot of sense. So if we wanted this to work, then we would find a way to really increase that residence time. Then we'd have more growth. Okay, so I just wanted to comment on that. I know there was at least one question there. Any questions or issues, concerns about flocculation sedimentation? All right. So that's it for the content that's going to be on the exam next week. And I have a few slides, probably go fairly quick, and a couple videos to give you the context of our next segment. So we really won't be going into any calculations today. So that way you don't have to stress yourself about that side of your brain as you prep for the exam. I hope to avoid any confusion there. But I want to give you the topical understanding of what is granular filtration. And so when we come back after the exam, we'll hop right in and start investigating that. Okay, so we're actually going to talk about two different types of filtration, one being granular and one being membrane. So a membrane, by definition, is something that allows some stuff through, but not everything, We talk about cell membranes. We talk about membranes in a lot of different contexts. In water treatment, what we're talking about is basically something that kind of looks like a very fine mesh, or something that just has some very small holes in it. So we pour water through, and any particle that was in there will get stuck on that surface as it makes its way through. It's a size exclusion. The particle is literally too large to make it through the space. That's primarily what we're talking about with membranes. On the physical side of it, it gets a little different when you go so far down where you're dealing with like reverse osmosis for desalination kind of stuff. Rejecting actual atoms, you're kind of size exclusion, kind of just chemistry, thermodynamics stuff. But we'll not worry too much about that. Primarily, it's a size exclusion. Even like screen for a window or a porch or something, that's designed to be a membrane that allows fresh air in and to keep mosquitoes out, basically, and other bugs, right? So that's the hope for a screen porch. For a granular filtration system, which is what we'll talk about first, it's a little simpler. We have some water, and we're going to stack it on top of basically some sort of a bed or chamber of sand grains. It would be a lot like kind of doing artificial filtration with groundwater, right? Groundwater kind of gets filtered because it's working its way through all the particles, the soil. Naturally, particles will get stuck to things along the way. Large things will get removed. But generally, water's flowing through the ground and kind of having some treatment, some filtration in that manner. So this is sort of an artificial way of doing that, where we pour water on, it fills up on top of this bed, and then just the gravity sort of pushes it down through the bed. What we're really doing here is not so much size exclusion. A lot of the particles could make their ways through the pore sizes. These are kind of, if we're talking about a really small particle, let's take this little piece of chalk, and then maybe my fist is a sand grain, right? So these are pretty small particles that could make their way through, but on average, they tend to have so much interaction that they might stick to another particle, they might stick to the side, and theoretically, we've already destabilized them with the coagulation, so they're already pretty sticky and ready to find some surface. And so we actually use a lot of adsorption type of phenomenon. Yeah, if we do have a large particle that made its way in, that might get mechanically screened out, but generally we've probably done sedimentation. That's not really what we want to be doing, so that's not the primary. Especially because we don't want it to get a layer of small particles just stuck on the surface, because then it's really hard to push water through. We're kind of blocking all the pores. So sometimes we might have a little internal flocculation happening inside, where one particle meets another, stick together, they're a little larger. Maybe then they're size excluded. Maybe they're just sedimenting as they make their way through the channels. It's like a whole bunch of tiny little sedimentation reactors. It can just fall out of solution, land on the next sand grain. Maybe they're you might call it intercepted. If you look, the particle kind of is intercepted at the edge. It's kind of flowing along, and it just kind of hits the wall. Or maybe impaction. The water through the pores makes a turn, and the particle is too heavy to make the turn that quick, and impacts on the sand grain. So all sorts of little ways to think about why this works to separate the particles. A lot of it may be pretty intuitive. Just a mixture of these different things happening. And so in practice, what this would look like, we can put it in kind of two different contexts. One is gravity driven, and the other here would be kind of pressurized. So we might see some sort of a treatment plant, or even like your swimming pool might have small little cylindrical looking filtration units, and chances are pretty good that they're packed with sand or maybe some activated carbon granules. It's kind of like charcoal, but small. The carbon filtration, the activated carbon, tends towards allowing molecules to stick. Something like if you had some benzene in a groundwater from like petroleum contamination, you probably pump that up through an activated carbon filter because the benzene would be sticky to it. I have in my lab this pilot filtration system with 3 columns here. They have a mixture of sand type stuff and activated carbon kind of stuff. So if you're curious, I can show you. We just have it set up to treat the tap water. We're not actually using it for research. It was sort of donated for teaching purposes. So if you are, fascinated by this or want to come see it, let me know. We might actually be loaning it out to do a study on different water treatment techniques for St. Tammany Parish. They have a new well water supply. They're trying to figure out the right treatment for it. So this might actually get some field action pretty soon as well. So again, let me know if you're interested in any of that, and I'll keep you in the loop. It's kind of neat because we can send it through the backwash cycle and see all the particles kicked up, and we haven't really cleaned dirty water with it, but just like when you first run a Brita filter, there's like all the little sand grains or like the little black specks. There's just a lot of small particles that happen to be there that might come out at first. Well, you can see those backwashing and kind of coming back out. So it's a pretty neat thing. Otherwise, the more typical, at least for drinking water, would be to fill up a large, kind of like a large swimming pool type of area, and layer sand grains down at the bottom. Have some sort of support system, maybe some larger grains to hold up the smaller ones, and be able to run water basically vertically down through it and have a way to distribute water on top of it, let water push its way through. So we'll see a couple of examples of that in a few minutes. Okay, might just look like this. Might just look like some water sitting there. You're not sure what's going on, but this is active filtration, where maybe it's each one of could be each one of these, although I think so that could be a filtration bed. It kind of looks to me like you can actually see under these walkways, so maybe these are the beds shaped like that. Regardless, that's kind of what it would look like in some sort of a treatment plant. Okay, so a quick bit of context for granular filtration in general. These days we would call this rapid sand filtration. Would be a common term for it. Even if we're not using sand, it's essentially the size of sand grains. So this is a catch-all term for that. Rapid is just a term we use because the alternative, which we kind of started using even back in the 1800s, is to pour water over a bed of sand and let it slowly seep through and actually let biological processes handle some of the junk that's in the water. And that's a lot closer to just artificial groundwater kind of a situation. So in that case, I mean, normally we try not to need biological processes for drinking water because that means there's a lot of junk in there, and then we're also growing more bacteria. But if you had a better way and you had some stuff in the water that you needed to degrade, I guess that could be a possibility. Okay, so these days the only time a slow sand filter would ever be used is specifically for biological treatment in a very, I guess, resource challenged area where it just makes sense to flood a bed of sand a little bit and kind of let it do its thing. Okay, so then when we talk about the actual operation of some filtration and a filtration cycle where we're pouring water onto the filter, eventually it gets clogged up and we need to backwash it. And then when we have it fresh and new, we're starting a new cycle. Early on, there's still some junk coming out because it all got shaken up and not everything made its way out in the backwash. This is what we'd call a rinsing or ripening stage. Like the first few minutes, you have a new Brita filter and you're getting little black specks and you don't want to drink those. So you'd pour a few gallons of water through first, right? That's the filter ripening stage. So that's like the early operation. If we were to draw like a cycle time, we would have a little bit of rinsing or ripening here for a few minutes. Then we'd have some period of filtration. And then we'd stop it for some backwash and repeat the cycle. Okay, so backwashing, pretty obvious. We're just reversing the flow of the water. It's going backwards through the system to kind of eject all those particles that got caught up in there. A couple of other terms here, head loss. What we're talking about is if we're adding water on top of that filtration bed, the hydraulic head or the pressure, the height of the water, pushing the water through will naturally increase as it clogs up. So what we do to keep a constant flow is we give it a constant flow, and then basically gravity adjusts for us and says, okay, well, if it's not flowing as fast anymore, the water level will just build on top of it to pressurize it and push it through to keep basically a constant rate of water going through. So it's actually pretty convenient that we can just load the water on, and it's doing that filtration and accounting for this head loss, the loss in pressure there, or the increase of pressure drop across the filter to keep our filter operating like we want. Last one would be turbidity. We've talked about turbidity already. I think I probably showed you the slides I'm about to show you, but basically it's a measure of how many particles are there, and we want to be monitoring turbidity over time to make sure that as we're doing the filtration, if we see a certain condition that particles are making their way out, we would stop and backwash, right? That would be an indicator to say, okay, now it's time to stop. So there's really 2 or 3 indicators, and we'll talk about them in a little more detail, but to know when to backwash could be just a time. At some time we decide every 24 hours. We'd also be monitoring the turbidity. Okay, if we're getting particles coming out at some level, we're going to stop. It's not safe. We need to we need to stop that treatment. And then sometimes head loss. If it takes too much pressure to get water through, we run some risks of channelizing the filtration bed to create a fissure in the sand. It'll kind of push it apart and create like just a direct route of water to go straight through. That will also make it so a lot of particles are just going to fly right through. So if we're monitoring turbidity, we should notice if that were to happen. But usually in practice, the types of sand you're using and all that, they should be rated for some amount of pressure that they can generally handle with no problem. So you keep it within, you keep your operation within that limit. Okay, so turbidity. Maybe we're taking water that looks like this second glass here, and we are filtering that to achieve water that looks like this first glass, right? 0 turbidity or very low turbidity. And then when we backwash, it's probably going to look a little more like this or even worse because we've collected all those particles and now we're dealing with those. So that turbidity, that high turbidity scenario, that backwash, definitely sending that to a wastewater treatment and not reusing that, not doing anything. That's kind of removed from our system. That also means, as we'll see later, that we are actually treating some water, and then we have to use that treated water to wash our filters. So there's some amount of water that we produced that is now wasted because we have to backwash it. So when we do our calculations later, what we'll see is what we're really calculating for is, on the whole, how much water are we getting for each filter? And how do we account for the time that it's spent not filtering? How do we account for the amount of volume of water we wasted that we had already filtered? And likewise with the rinsing, we also have to send the rinse water to the trash, basically, to wastewater, because it's also coming out with too many particles. Okay, so turbidity is just kind of that light scattering thing. I think we already talked about that, where you can kind of use this one metric to see how far down you can actually distinguish the colors, and use that as how many particles are in there, because the distance that the water is traveling gives us an amount of light that's going to be scattered given how many particles there are. So if you were to drop this kind of thing in a very murky basin of water, it'll disappear rather quickly. If you got really clear water, you can see it pretty far. Sort of just visibility. Okay, so I mentioned this, but the keys to say when we're going to backwash, we almost always use turbidity limits in addition to one or the other here. So sometimes we might do a head loss, sometimes a time limit, but I think our regulation says we should always have a turbidity monitoring going on. All right, so if we were to track turbidity over time during a filtration cycle, we would actually see during the rinse, and what I'm going to do is I'm going to say we're going to go from rinse to some cycle end point. We'll find that in a moment. And we're going to have some limit, some turbidity limit here. And if we look at what's happening during rinsing, we're probably above the limit for the most part, because we've got these extra particles we don't want in there. We just backwashed it. The granular media is all shaken up, and there's still some particles that are loose, and we need to rinse out. So at first, we probably have too many particles above the limit, but in the next few minutes, it should probably drop to some point where then we kind of have our starting point for operation, and then it's pretty good for a while, and eventually we have it kind of start climbing, and eventually we reach the limit and we say, okay, right there, we've hit our cutoff, and we're going to stop treatment. So on our timeline, all of this would be filtration, and then we found our limit, and then we have to backwash. So then we do our backwashing step. Sometimes it will not just be backwashing. Sometimes you'll do backwashing and like an air purge, send some air through the media to shake things up even more, and then backwash. We'll see an example of that in a minute. Okay, another way to look at that would be to have a head loss limit. So again, if we drew some sort of limit here as the maximum that we want to go through, then we track our hydraulic head. We can look at it in terms of, again, with a rinse. We would see that in this case, the cleanest filter has the least pressure drop. With a clean filter, even though some particles are coming out with a rinse, it has a pretty low pressure. So the head loss is the lowest early on, and this would just slowly scale up as it gets dirtier and dirtier. And then we'd say, okay, well, we just hit the limit, so that would be our cutoff. And then we would do our backwash. So in all, a typical cycle, again, a lot of times we'll deal with it just as a time limit, but these are the reasons or the causes that would tell us, help us to define that time limit in the first place. So a lot of times we'll have some sort of a cycle that would look like this. We'd have some rinse or ripening. That's usually on the order of 10 to 20 minutes. We'll say 15 minutes. Then we'll have the actual filtration where we're producing water. That's anywhere from 24 to, 100 hours on the large scale. Then we reach some time where we have to backwash. And sometimes, I'll go ahead and add this in here, sometimes we'll do an air purge. As part of the backwashing sequence. And maybe this is 10 minutes or 5 to 10 minutes. And the backwash is probably something like 10 minutes. Okay, so in the scheme of things, we're spending less than an hour on the rinsing and backwashing steps, and at least 24 hours filtration or something like that. So the entire cycle time might be 24 hours. I think I've got a problem for next time to that uses that number. So you can imagine then we're producing good water for 95% of the time, and then we're taking a little bit of that water, sending it back through to rinse or wash. Okay, so that's kind of the deal with granular filters. The math is quite straightforward. It's not even true like mass balancey kind of stuff, we'll find. But it does kind of put us in the right thinking for a flux through some area, and that's actually going to be helpful when we talk about membranes as well. So for now, the last things I want to show you is a couple of videos. Any questions right now, or feel free to ask them with the videos. We're just going to watch some backwashing. I'll skip through them a little bit, so we're not here for watching the grass grow for a long time. Oops. Okay, and let's see about volume. Okay, so this first one is going to be air purge and backwash directly. They don't complete the process in the 6 minutes, but here you'll see the air purge is about to begin. There's water resting on top of a sand bed here. I'm going to turn off a few more lights to make that a little clearer. So this is literally, they're just pushing air up through right now, and then what they'll do this for a couple minutes, and then they'll have to prime the air out of the pipes that they were just using, and then flush with water. So I'm going to skip forward a little bit until they're done with that. It's quite noisy, and if I were to skip here right now, they'd all be mad at me because of the noise. So I'm going to try to skip past it. Nope, didn't quite make it, sorry. Here we go. All right, so they're done with the air purge now. They're priming the pipe, and they're about to start pushing water.
Film the water for a bit. It's all warm. It's all bubbly. This is how they make root beer. Giant.
This is how you make root beer. Okay. And you'll see why they say that. So now they're starting to push water through. There's still a fair amount of bubbles. So you saw this coming out. They fast forwarded a little.
Gonna do it. Oh yeah!
And now the water is overtopping. That's all those particles that were in the water and now they're concentrated in this background. The way these filters operate is that middle channel there, this is just basically 2 filtration beds. That middle channel, normally you flood with the water that you're treating, and it would go the other way. So you fill up that trough, you fill these side troughs, and just load onto the filters that way as we distribute water across. So in backwashing, they just reverse it, and they send this, they rearrange the pipe to send this to the waste. And so basically, they're just going to push water through it at this rate, which is a pretty good flow rate there, until it kind of clears out the particles, right? So that would probably take about 10 minutes. I have one other video I'll jump to, and what's neat is you can kind of see that the particulate matter itself may be different colors just based on maybe the natural chemistry or organics in your area, in the river you're taking from, or maybe even the coagulants that you're using to cause them to stick together. So we'll see a bit of a different color. An example in this one. And this is 18 minutes, so this is like the full cycle where I'll definitely skip around in this one. I don't think they're doing air purge in this one. So you see they've got a little bit of a different setup. It's still sort of a middle trough thing, and then a little indents to let the water overtop. Right now they're just about to start the backwash, so you see kind of that's just the media there, water sitting on top of it. And as soon as they start backwashing, you'll see the particulate matter coming out. Jump through a little bit. Okay, if you look closely right now, you start seeing everything sort of change colors a little bit. That's all these particles starting to just appear. So that's kind of a neat little transition right there. Suddenly, everything is coming out and looks quite a bit different. So I'll let this go for a moment. You see it'll start overtopping these things. Oh, okay, so they are doing air purge, I'm sorry. So that was that moment where air was starting to disrupt all of it. Okay, so I'm going to skip forward. You can see the particulate matter here is pretty orange. Quite different. And just like last time, at some point it's just overtopping here, and similar trough scenario, and trying to distribute the water fairly evenly across and going either way. All right, and I'm going to skip forward now. You know, as fun as that is to look at that, it is pretty neat to see. But what's really a little bit more interesting is towards the end of the cycle, when the filters actually start clearing up a little bit. Actually, doesn't take too long. You can start seeing spaces where it looks like maybe there's fewer particles, there's darker spots. And as we skip through, there's darker and darker patches where it's actually more clear water, and you're actually just seeing the media underneath. And so you see there's still some particles around, but it's certainly clearing until pretty much later. It's oops, back a little bit. It's nearly clear, and you see they stopped it here, and so now they basically stopped the outlet, and they're just going to use the water that happens to be there right now, reverse the flow, and start letting water out from beneath the filters, and just do the normal filtration. So that's granular filtration in a nutshell. That's kind of what it's all about. After your exam, we'll come back to this and talk about kind of how we calculate each of those pieces. So that's all I've got for you for now. So see you guys on Thursday.